NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D.
Welcome, everyone, to another episode of the High Impact Thesis podcast. Today, our guest is Anik Naha Biswas from the School of Electrical Engineering. Welcome, Anik, to the podcast.
Thank you so much for the invitation. It's an honor for me to share my research ideas. So, hi everyone. So, I am from EEE department, and right now I am doing my PhD. I am in the third year of my PhD, and my research topic is rainfall forecasting using GPS signal.
So let's start from the beginning. So why did you initially choose to work in this area?
So, actually, as I have already told, that my research topic is rainfall forecasting using GPS signal. So, from my BTech, actually, I was a bit intrigued by the idea of satellite technology and satellite communication. And when I came here, and my prof offered me two different topics. One is this one, and another one is the design of antenna for animal tracking. So when I listened to this research topic, so it caught my interest as I am already a bit inclined to satellite communication and satellite technology. And then I did a bit research about it, and so that's why I first of all I chose this one over the other. And also another thing that I want to say, that weather forecasting. So though I am focusing on rainfall forecasting, but on a broad aspect, if I want to say from a broad aspect, that weather forecasting is quite important in our day-to-day lives, as we all know that due to pollution or due to global warming, the climate is changing so rapidly nowadays, and especially in the Pacific islands like Philippines, Japan, or the western coast of USA. All these places experience a lot of cyclones, hurricanes, and with torrential rain. So this causes a massive destruction of human lives and public properties. So it's very important to predict this weather phenomena before, so that we can at least minimize the destruction, the casualties. And also a place like Singapore, where we know that the weather changes so rapidly, means that anytime there can be a rain event. So for this, I think weather prediction is quite important, and also this research area has a lot of demands right now. So yeah, that's the main motivation why I chose this.
Did you have any previous experience with satellite technology communication?
Actually, I did my masters in communication technology, microwave and communication technology. So mostly I studied satellite communication, but I didn't have any hands-on experience or any research experience on this topic, because in my masters I mostly worked on antenna and frequency selective surface. So that's why I had a very basic overview about this topic. And yeah, so I had an interest, but yeah, I got that opportunity to explore. So when I got the opportunity here, so I just grabbed it.
Mm-hmm. So I think we've already had a similar topic before, but can you tell us again, or remind the listeners, what can we do with such technology, in relation to weather forecasting? So, what's the relationship between GPS communication and the weather?
Yeah, so that's the main research topic, means rainfall forecasting or weather prediction using GPS signal. So we all know about GPS, that it's global positioning system, global positioning satellite. Sorry. Yeah. So what means we all are quite familiar with this word. It's wherever we go, if we don't know our path or on destination, we just take out our smartphones and it navigates the way. So how does it do that? So it receives the signal from the GPS satellites, and then it tracks our location, and it shows us the path to our destination. So we are using the same technology for the weather prediction. So means when we are trying to estimate the location for a particular user, we measure some particular atmospheric parameters what we actually use for positioning purpose for positioning. But here I am using the same atmospheric parameters for rainfall forecasting. So if I want to explain it in a bit detail, so then I can tell that, okay, so when the GPS signal is propagating through the atmosphere from the GPS satellite to the receiver, it actually gets delayed. And the main reason there is that the refraction. So we all know that when the light ray propagates from one medium to another, so there is a difference in refractive index and it gets bent due to that refraction. So the same thing also is applies here. The electromagnetic wave when it propagates, it actually propagates to different atmospheric layers, and due to the difference in refractivity, it also gets bent. And mostly we calculate this delay to measure the other atmospheric parameters. And same thing also we apply to means detect the location of a particular user. But here I am not detecting the location; rather I am using those parameters to calculate the amount of water vapor in the atmosphere or any other atmospheric parameters to predict the weather.
And like, how many satellites do you need for accurate estimation? Like, is it the more satellites you use, the more accurate you get?
Yeah, of course. Actually, for if I consider about the look positioning, then at least it requires four satellites, because one satellite can never, because so we know that when I am doing the positioning, there will be three parameters. That is not three parameters, with three unknowns. One is the longitude, latitude, and another one is the altitude. So at least we need three satellites, but there will be other unknown variable, that is the receiver clock error. So at least we need four satellites for the correct accurate estimation. But as many satellites we will have, the more the satellites we will have, more the accurate estimation we will get. Similarly for means weather prediction also. So for weather prediction, when we calculate or measure the atmospheric parameters, it actually we don't do the processing. There is a software named Gypsy. We or there are other softwares as well, like Barneys or Gamut. So we use those softwares for the processing, and those softwares actually take the data or the observations from several satellites, because it requires for convergence. So more the data we will have, the convergence will be better. And as the convergence will be better, then the results will be more accurate. It's something like so convergence. It means something like if we are talking about any Newton-Raphson method or any Euler method, where we need some we so we want to solve some differential equation, and we want to solve the differential equation, and there we need means we need some iteration. We solve the differential equation using some iteration, and when the solution gets converged, then we means give an estimate solution for the for the differential equation. It's also similar, quite similar like that, but here this software takes the observation from different satellites, and they use the least square estimation to solve that. So more the satellites will be, more the accuracy will be we can obtain from the result.
Mm-hmm. And in terms of the like on the ground, how does it look like, the number of stations, or the like? Do you need to have multiple stations within an area to do accurate predictions, or one would be enough?
So it's so yeah, as you have already asked me, that I have already means worked on both the conditions, that using a single station as well as using multiple stations. So my first work was based on a single GNSS station. So for a single GNSS station also, we obtain the data for means if we are considering a single GNSS station, then also we obtain the results from different satellites, and then we process it, and more the satellites we will have, more accuracy we can achieve. So that's the one thing. But also we can means we can analyze the data for different stations, or maybe for a very larger area. So we don't want to just want to analyze or want to we just don't want to analyze or restrict our of our results or our study to a particular station, but at the same time we want to expand our area, expand the size of the area, the size of the region for which we want to predict. So for that we require more number of GNSS stations.
I see.
Yeah, but also this is a problem if I talk, because this is a challenge for us, because the dense network, always we don't have a very dense network. So maybe I have the data for Singapore, but I don't have the data for maybe Batam or maybe Bintan. So always that's a challenge for us, but yeah, we are working on that to also to predict the weather for a larger region as well.
So, like for a single city, for example, let's say Singapore, like would one station be enough, or would you need multiple stations within Singapore, like 2 or 3, to do accurate estimation of the moisture in the atmosphere and so on?
So means so the availability of data is a challenge in our field always, because there is one server, that is international GNSS service. So from that we can obtain the GNSS data at free of cost. But this server has only 500 stations all over the world, and there is only one station in Singapore. So for that, if we want to predict the weather, we have to rely on that. But Singapore has its own GNSS stations, which is not free. So if we want to obtain the data, we have to pay them and to get that data from them. So this is one thing. So this is one challenge, that availability of data is not that easy in our research field. But of course, if we have more number of stations, then we can the weather prediction or the algorithm will work better, because sometimes, because we know that in Singapore the weather is a bit localized and it changes so rapidly. We all have witnessed that maybe there is it's raining in N2, but if you go to the city, it's completely dry. There is no rain.
Yeah.
So it's quite it's quite localized. So maybe if we have a station, so the GNSS station that we use mostly, it's especially located in NTU. But if I want to predict the weather for anyways, or maybe for Changi, then maybe NTU data will not be that accurate. So more number of GNSS stations we will have, it will be more
beneficial.
Yeah, more beneficial or more accurate.
I see.
And what about the time window? Like, how far in the future can you predict? Is it
So
hours, days?
So that's another thing, we can say that's another challenge. So GNSS means the weather prediction using GNSS technology is not a very old method, but means researchers are working on this since last 1 or 2 decades. So the first method that they used for weather prediction is measure the amount of water vapor in the atmosphere. But there is a challenge. There is a loopholes in that method, because water vapor generally starts to rise, especially in tropical region like Singapore. It starts to rise 2 or 3 hours prior to the rain event. So we can only measure the water, we can only we can see the change in the water vapor in the atmosphere just 2 or 3 hours before. So even if we set a threshold, this water vapor will cross the threshold just few hours before the actual event. So maybe the prediction window will be for 2 or 3 hours max to max. But that's why we are working on my research actually not just to calculate the amount of water vapor, it actually focuses on another parameter, that is the change of uh, atmospheric refractivity in the horizontal direction. So that is the, which is actually technically called atmospheric gradient. So it means the change in horizontal refractivity. So I am actually looking on this parameter, because to first thing, to propose a long term weather prediction model, so that at least we can predict the weather 6 to 12 hours before the event. And also there is another thing, is that water vapor is something, it's a scalar quantity, but this change in refractivity or in the horizontal direction is a vector quantity. So it has a magnitude as well as a direction. So we can, at least we can, if we just propose a particular threshold value for that, then we can see that whether this atmospheric gradient is crossing that threshold, or at the same time, what's the change in the direction of this atmospheric refractivity. So from this we can say that, okay, there, if it had crossed the threshold, then there might be a possibility of rainfall in at this particular location. At the same, also we can say that the direction is changing maybe from east to west. So we can say that, okay, the weather front or that rain band is actually approaching from west towards east direction. So these are the advantages that we can say that we can also predict the rain, as well as we can analyze or we can observe the movement of that weather front.
Yeah. So you mentioned the few of the challenges that you face. What about noise and like unwanted signals? Do you have those in your data as well? That do you need to filter your data from sources of noise and error?
So first thing is that actually I'm not working on noise, because it's it so there, first the signal is received by the receiver. So means who are working on the GPS receiver, it's mostly their job to filter, to means design the receiver in such a way that it can filter that unwanted signal, because the frequency that we use for GNSS signal is either 1.5 gigahertz or 1.2 gigahertz. So it means the receiver should be designed in such a way that it can actually differentiate between the GNSS signal and any unwanted EM waves or any other cosmic rays. But yeah, there are some, means we call it that residuals. That is, it mainly is caused due to the multibar propagation. So that is, you can say, a sort of noise in our estimation. So residual or multibar propagation means when it's propagating, a signal is propagating, it might get scattered, or it might get reflected from some maybe some skyscrapers, or maybe some trees, or maybe aeroplanes. So that is the unwanted thing, that it's not, that's, or it might get also diffracted, a signal might get diffracted. So these are the main reason for this residual, or we can say that this is some multiple propagation. So means we we mostly expect that the receiver will receive means line of sight, not line of sight propagation, I shouldn't say line of sight propagation, but receiver will receive one particular signal that is coming from the satellite, but it can receive some other reflected or diffracted signal as well. So that is a kind of noise in our estimations, and we call it as a residual. So also, yeah, and as you have already asked before, that how many satellites do you require? So if we have more number of satellites, then we can solve these equations. We can, because there will be several unknowns. So more number of satellites means we can solve those unknowns more accurately. So, and this is one thing, that this is a type of noise in our estimation, and we need more satellites to converge the solution so precisely.
And do you also have to consider the the topology, the geographic location of the area that you're analyzing, or do you just simply apply the same algorithm to different places?
Yeah, that's a very good question, because weather is, it's something in atmosphere is something like a hidden treasure. We don't know what's happening there. So maybe the weather or the algorithm that I am proposing for Singapore, it might not be applicable for Kuala Lumpur or maybe in any place in Indonesia. Maybe Kuala Lumpur and Singapore both are in tropical region, but it might not be applicable for any subtropics or any temperate region. So that's why, and also for different years it might change. Like there are some other weather phenomena means other weather phenomena like La Nina, El Nino, or median Julian oscillation. So it also affects the weather a lot. Significantly, it affects the weather. So that's why, I mean, sometimes you should consider those things into your algorithm. So we cannot say that, okay, I have proposed some algorithm for based on several data for a particular station, but I cannot say that, okay, it's a global empirical formula or global empirical algorithm that can be used anywhere. So okay, maybe the it might happen that the algorithm, the method might be different, but the threshold will vary from place to place or from year to year. Maybe we can, maybe if we go to some other region, maybe we need to introduce some more variables as well. So that's always a challenge. So we can say like, I have proposed one model and it's an global model. It can be used anywhere. It might can be used, but it needs to be modified for different years and as well as for different regions as well.
All right. So yeah, I think you gave us a good background about using satellites for weather prediction and so on.
Thank you.
So now we'd like to move on to your own personal work. So we want to know, what is it that you do on a day-to-day basis? What kind of tools you use? What's your research focus? If you can speak to that, like what's the specific objectives or aims of your work? If you can share with us some of that.
Yeah. So I mostly I I have already said that I obtain the data from one server. It is International Genesis server. I obtain that raw data. It's called a Rhinex file. I download those Rhinex files from there, and then I process it using a software which is called Gypsy. And there are some other softwares like Barneys and Gamut. So this, after processing those Rhinex files, I get the ultimate or final products or final estimated values for the atmospheric parameters.
So what are you looking at? Like for what atmospheric parameters are you?
So there one atmospheric parameter is called PWV. That is so okay. So I actually we need to measure PWV, but for that we have to calculate that parameter that I obtained from that software is ZWD, that is zenith wait delay. So it's the delay of the GPS signal due to that water vapor present in the atmosphere. So this is one parameter. Another is that parameter is called residual, that I have already said. It's a kind sort of noise in our estimation. It caused due to that multiple propagation or any other unwanted reasons. So this is one parameter. Another thing is that I am working on is atmospheric gradient. So it's the means difference in is the change in atmospheric refractivity in the horizontal direction. So as I have said, that signal will get delayed when it will propagate through the atmosphere. But the thing is that it will, when we are talking about this, we are mostly considering the vertical atmospheric refractivity. So means the change in atmospheric refractivity in the vertical direction. But there will be a change. So in earlier days, researchers assumed that the atmosphere is spherically symmetric, but it's actually not so. So when we will move from one place to another place, means maybe we are going from NTU to NUS, there will be a slight change in atmospheric refractivity.
Sure.
So that's the different change in azimuthal direction, or we can say horizontal direction. So this is my main parameter that I am focusing on, and it's like it's a vector quantity that I have already said that we mostly look at the magnitude of that parameter as well as the direction, how it's changing and from where to where it's the orientation is actually changing. So this is the main parameter that I am focusing on, and after obtaining those values, I use the some basic statistical analysis. So I write a code in MATLAB, and after writing the code, I do some basic statistical analysis like some histogram plot or some median mode values. I try to calculate, and based on that, I set a threshold for the rainfall. Means if the parameter crosses this, the magnitude of the parameter crosses this value, then there is a possibility of rainfall maybe within next 6 hours or so.
Oh, I see. And would it be possible to get like a map showing you the distribution of the, I don't know, clouds or moisture density over a over in a specific area? Would it be possible using the data you obtained from?
Yeah, actually, right now I am doing that. I am trying to create one atmospheric gradient map. So maybe I am taking the tropical region for especially in the Southeast Asia, and then I am trying to plot the atmospheric. As I have said, it's a vector quantity, so I can plot it in terms of an arrow.
Yeah.
So the length of the arrow represents the magnitude, and and also the direction of the arrow will actually represent the orientation of that parameter.
I see.
So like that, we create that atmospheric gradient map, and based on that, we can see that if we just create several atmospheric parameters, several map for atmospheric gradient for some consecutive maps, maybe for 6 hours or maybe for 12 hours. If I just
over time
plot over time, if I plot those maps, then I can see actually I can see the changes of that atmospheric gradient, and based on that, and also I compare it with the precipitation map. Also, precipitation map is that rainfall rate over the same region, and when I compare these two, then I can analyze, or I can conclude that okay, so rainfall is coming from east to west, and similarly this atmospheric gradient is also changing its orientation in the same direction.
I see. It's clear now. And other question.
So, when you are writing your codes and doing the statistical analysis, how do you validate your results? Like, if you are expecting certain percentage of rainfall in certain area, like how do you validate?
Yeah,
Is it from the station, or do you use different methods?
no, it's a good question actually. I obtain those rainfall rate from weather station. But if I want to, because as I've said, the data availability is a really challenge in our case. So means if I want to analyze the weather for some other regions, it's not very easy to obtain that rainfall data for that place. So right, actually there is one precipitation map that is available on in the website, and we use that precipitation map, though it's not the exact rainfall rate, but it's an average rainfall rate over 3 hours. So I right now, when I am looking for a larger region, so I have to rely on that. So we so it's something radar data. So it's the rainfall rate is calculated based on radar data, and it's an average value over 3 hours. So I mostly use right now. I am using that map, and as you have said that. So based on that, I mostly what I do, I plot two type of curves. One is before rain event, and another is before during no rain hours. So based on that, I try to I try to observe the separation between these two curves. If there is a separation between the two plots, it means, so I plot the histogram plot, and means histogram means not like a bar histogram, it's a continuous histogram plot. And then when I just observe the histogram plots, then I try to see that whether there is a separation or not. if both the curves are quite overlapping, it means that there is no difference, or there is no difference in values during these two period, in the dry period and the wet period. But if one curve is a bit right shifted, another curve is a left shifted, then we can say okay, there is a difference. So when there will be rain, maybe these values will start to increase. So like that, we set the threshold value. But another one very important challenge that I faced, that how to means define a rain event. So means suppose I have some value, whether anything is greater than zero will be considered as rain or not. So that is always a challenge. So for a particular station, we can means based on some previous literature, we set up threshold for a particular station, because we have that data for every 5 minutes. For a means when we are considering a what means when we are analyzing the results for an individual station, then we have the data for every 5 minutes. So like that, we can set a particular rainfall rate. But when we have the precipitation map, then sometimes it's a bit difficult, because I am not considering a particular station, I am considering a large region. So then maybe within that large region, if I consider a grid, and maybe within that grid, suppose so one grid, so how I do my own research is, for each grid is equivalent to 1 degree latitude or 1 degree longitude. And it so if I am considering a suppose 8 cross 8 grid, it means 8 degree latitude and 8 degree longitude in horizontal and in horizontal direction. So for that 8 cross 8, so it's a 8 cross 8 window, so there will be 64 small cells. And so based on that, I do some statistical analysis, that whether which what should be the criteria for that. Suppose if anything, suppose the first criteria that I said is anything greater than zero. So if I find anything greater than zero, then how many cells should I consider for that? If or should I consider 80% of the entire window? Should I consider 90% or 70%? Like that, I just try to vary, and like that, I just try to vary, and based on that, based on some statistical analysis, I set a rainfall criteria for the rainfall and for no rain. Suppose if it's more than 70%, maybe it will be considered as a rain event for that larger region. But if it's less than 30%, then we won't consider it as a rain event for the entire region. So like that, I try to set that result.
So you said 8 by 8. That's 80 by 80 kilometers. I mean 800 by 800. That's a huge region. Is that
Yes.
the kinds of area you're working with for predicting? Like that seems like one data point for the whole of Singapore. Is that how? Am I understanding it correctly?
Yeah. Actually, it's true. So it 8 degree means 8 degree, 8 by 8 means almost 800 kilometers. So that's it's up means I am giving an example, but yeah, when I analyze the data, so I saw that it's 8 cross 8 is not it's a good window size. So maybe we can estimate, we can analyze, or we can predict the rain for maybe in a very accurate way, because if we just consider one parameter or one feature, then it won't be a very good prediction algorithm. So we need to consider several parameters, and when we are considering several parameters, then we can consider a very big window. At least we can consider 4 cross 4 or 6 cross 6 max to max. So beyond that, I saw that the result is not that good. Maybe it's good for one parameter but not for the other one. So like that, we have to means make a trade-off between the window size and the efficiency that we obtain from that results. So maybe 400 kilometer, because I am actually, my main objective is looking for a larger region. So for a larger region, maybe 400 or 600 kilometers I want to see.
So right now you're working with the 8 by 8, or that's what people use? Because I was asking whether you use the 8 by 8 that you mentioned, or is it just an example?
it's just an example.
All
So
right.
I mostly vary my window size from 2 cross 2 to 12 cross 12.
Hmm.
And based on that, I try to choose one, but means I try to optimize the window size where I am getting the best result.
Okay.
For which windows I am getting the best result for all the parameters that I am using.
Okay.
Mhm. And how long does this process take from getting the data all the way to?
It depends. Means
Visualize.
like for this, when I was working for a larger region, it took several months because I was not getting the result. So whatever I was trying, it was not giving me any conclusive result. So I was like, it was quite frustrating for me as well because at because means I it was there was a time when I didn't get any result for consecutive 2 months. And after that I changed the parameter and suddenly I got few results. And it also happened once that I got a very good results, but then when I changed I increased that sample size or I included more number of data points, then I didn't replicate the same result. So
So
it
there's
is
a lot of uncertainty.
there is an uncertainty. So there is a quite uncertainty. So that's why right now I am using for 1 year data for a long region or large region, and it's includes like almost few large data points. So based on that, I am getting some good results, and hopefully it will be same for if I include more number of data points. But before I started with very few data points, and then I couldn't replicate the same result for a very large data set.
And is this a group effort or is it individual? Like,
It's
do you have
okay.
colleagues
No,
working
I
with you?
have one postdoc in my team
Hmm.
who works with me. So if I can't do anything, I face any problem, I just mostly I consult with him.
Uh-huh.
So Anik, you keep talking about not accessing data, but since every phone has GPS, it's a potential data source. So what kind of data do you actually look for? Oh, because the data received, what you've been saying is that you want GPS receivers, and the information that the GPS receivers receive, that is the difference is how you process it. In other words, a phone receives it and processes it to tell me where I am, but you get the information and you process it differently to get weather predictions. So my question is whether the receiver is the same, as in could it be the same? It's just that you're going to process it differently for your own purposes, or do you need a unique, or do you use a unique kind of GPS receiver that?
Yeah, actually, it's a really interesting question because our GPS, for our phone receivers, smartphone receivers, GPS receivers is not that powerful. So what we actually means how does our smartphone work? Smartphone navigate our way. So it just calculates the time that the GPS signal has traveled from GPS satellite to receiver, but it doesn't calculate the other important parameters. So when we are talking about a very precise point positioning, so precise point positioning, or we are talking about some atmospheric parameters, our phone receivers is not able to calculate those atmospheric parameters because for those atmospheric parameters we need some more more powerful receivers which can receive the data, and then based on that receiver we will process using a software, and then we will obtain the data. But our phone mostly it can calculate the time that the GPS signal has traveled from that satellite to the receiver, and based on that, so because when the satellite sends a data, it also sends its position and its clock information, satellite clock information. So based on that satellite position and satellite clock information, our phone can just tell that okay, so I am receiving that data at this particular moment. It means it has taken this amount of time to reach, the signal has taken this amount of time to reach to the receiver from the satellite. But it cannot process or cannot because when we are talking about some precise point positioning, we need or any other atmospheric parameters, then we need some other important and very powerful receivers, because for that we just not only we are calculating the travel time, we have to calculate the delay in the signal. Because based on that delay we will actually we can say that the precise measurement of our location. So our phone cannot exactly say that whether you are exactly means it can say that I am at, maybe it can say that I am at Yunnan corner right now, but it cannot exactly say that I am inside this room or I am just means inside the other room or not. So that's when I need that much of precise information. Then I need a very powerful receiver which can actually process those information very accurately. Because
So powerful here literally means more, like more energy. Is it? It consumes more energy. This receiver is that what you mean? Or it's able to clean out the signals better than the phone? Or what does it mean? More powerful GPS receivers.
Was it in terms of resolution, maybe, perhaps?
yes, one is the resolution, and that thing is that means we need when we have to mostly we have to calculate the signal delays. It will be in a very few millimeters or few centimeters, but we have to precisely we have to measure that atmospheric delay that has occurred. So our phone is not that it's not able to measure that very accurately.
I see.
So because actually the delay means the time that the signal should take to reach the receiver from the satellite. That is the time that it has taken, and the delay is the extra time that it has taken to travel. But that delay is actually responsible for that few millimeter or few centimeter error in our position.
Okay,
And
so sorry.
yeah, and so from that delay, we mostly we measure the amount of water vapor, because the delay is mostly cause the amount of water vapor or change in refractivity or in. And not only water vapor is not the only thing that is responsible for the delay. There are other things and other components of the atmosphere like gases, aerosols, the dust particles, snow. These all are responsible for the atmospheric delay, and this delay is in a very few millimeter or few centimeter range. So that is quite important to measure properly and to detect. And then if we when we process those data, then we obtain the results, and based on that we actually can do a very precise positioning or the weather forecasting, whatever we want.
Okay, so I'm actually trying to like visualize the path of the electromagnetic wave, like from the satellite all the way to the receiver. Like, can you tell us like what will be the difference between clear sky, no dust, no water particles, versus a lot of humidity, a lot of rain, like
Yeah,
water
so
vapor.
if there is water vapor, there is humidity, then there will be a change in refractivity, because the water vapor will change the atmospheric refractivity, and that's why the bending of the signal will be different. So if it's a clear sky, then the bending will means if it bends like by X millimeter, maybe if there is water vapor, it will bend like in bend by Y millimeter. So there will be a difference in the bending if there is some water vapor in the atmosphere. Dust particle, some atmospheric gases, aerosols, these are a bit quite obvious that will be there in the atmosphere. So there are actually two type of delays. One is hydrostatic and one is weight delay. So hydrostatic delay means that is caused by the atmospheric gases, dust particles, or aerosols. And this is the main delay. The main delay actually in the atmospheric delay, it contributes 90% of the atmospheric delay, but the rest of the 10% of that 10% atmospheric delay is the what weight delay that is caused by the water vapor. And this is a very random. We don't know what will be the exact amount of that weight delay. So there are some empirical formulas to calculate the hydrostatic delay, but there is no such empirical very accurate empirical formula to calculate the weight delay. So that is actually you have to uh, process. You have to measure that using after processing that raw data using in a software, because the software actually calculate the it. So it takes the observation, that delay observation from the receiver, and then it can calculate the hydrostatic delay in using that empirical model. And the difference is not only the weight delay. There is an equation, there are other parameters, other terms as well. So based on that, there will be some six or five or six unknown parameters based on the. And so they use some least square estimation technique. They take often they receive the observation for different satellites, and after means using those all the observations, all the values that they have, that has been calculated, based on that they use the least square estimation technique to calculate those unknown variables. So this weight delay is actually responsible for precipitation, because water vapor is the main parameter which causes the rainfall. So that is our main objective to calculate.
Okay, so let me see if I get this straight. So you have the receiver, and your algorithm, it depends on the fact that the receiver knows the actual time the signal should take, right? So when you receive a signal, so if you're trying to determine the position of a receiver, you only care about the time difference between the
Time
stamp
difference,
time
the
and the
stamp
receiver.
time of the receiver, and the time when the signal was transmitted.
But if you're trying to do weather prediction, you also care about the difference in the receive, like the delay in the signal.
Delay
right?
in the signal.
Yeah.
That is
So you
also
have
quite
a
important.
reference.
Not only for weather prediction, also for precise positioning. Because if you just calculate the delay in the signal, you cannot precisely you can measure someone's position. So as I have given the example, you can only say you are near to Yunnan corner. If we see it from in our
That's because of the delay.
That's because of the delay. So that's the precise positioning.
Mm-hmm.
So if we use more number of satellites, then the calculation will be predict or means the measurement of our location or coordinates will be more accurate, but still there will be some error in centimeter or millimeter. Maybe it can show that I am near to Yunnan corner or I am at Yunnan corner, but it can say I am inside or outside the Yunnan corner. So it's something like it's called a precise positioning. Or yeah. So and this precise positioning is not a very it doesn't give you a very huge error. So it won't give you a error in terms of meter or kilometer. It will just give you the precision in terms of millimeter or centimeter or max to max decameter, like that.
And from this delay, you're saying the water concentration in the air only contributes to 10% of the delay.
10%.
Okay. That seems like a very difficult.
Yeah, that's a very difficult thing, but because we can actually, the 90% thing, 90% delay is not that random. It's can be predicted using that empirical formula. Of course, there might be some error, but it can be predicted, or you can at least calculate it using some formula. But that 10% is quite random, because you don't know the amount of water vapor in the atmosphere, and it caused by this delay mainly is caused by that water vapor, amount of water vapor present in the atmosphere. So it's quite random, and that is actually mostly responsible for the rainfall. So there are some other parameters: atmospheric delay, and then residual. That's the noise part. That is the means that from multipart propagation or from some other, from diffraction or scattering, that we. So these terms also contributes to the delay. So total delay is actually the sum of hydrostatic, weight, atmospheric gradient, and the residual. So if our smartphone receiver is not able to differentiate between these small terms, it can only calculate the difference in the time from the satellite and the receiver time. It can calculate the difference between the satellite time and the receiver time, and based on that, it can calculate the travel time of the signal. And the satellite also sends its position. So based on that, it can calculate the position that. So it's something like that. It's quite similar to the radar technology. So radar also works somewhat similar to this. So it that sends a signal, it gets reflected back, and it calculates the travel time, and based on that, it can tell that where the actually the object is located. So it's also somewhat the concept or the idea is somewhat similar to that.
But I mean, coming back to the smartphone mm, question, like, because I mean, most of us are are not moving most of the time, right? Like we are most of the day we are staying approximately in a small, we cover a small region. So wouldn't it be possible to collect the data from several smartphones and compare the delay between the smartphones rather than the delay of the signal itself? Would that be
Yeah, so
possible?
you are talking about the differential positioning. Someone you are talking about the differential positioning. So yeah, it might be possible. Maybe uh, maybe right now it's not. We don't use that powerful or high resolution receiver in our smartphone. Maybe in future it will be possible, but right now there is some tech methodology called the differential positioning. Means it's not we use two different receivers, and one done means coordinate of one receiver is known to us, and based on that we calculate the coordinate or the location of the other receiver or the user. So that's called differential positioning. So maybe we can implement the same method, the differential positioning in smartphone. Maybe we right now in this room we are four people are sitting in this room. Maybe using the location of this the uh, maybe using the data from these four smartphones, we can we will be able to means remove the delay of the signals, and based on that, might be in future we will be able to use our smartphone to predict the weather. But I don't know when it will happen in reality. But yes, there
Right.
is
But
it might
in
happen.
principle, like let's say you were mentioning like NTU and the US and like Changi, like if you have if you're using, let's say, the smartphone receivers in these locations, and then you can figure out that there will be, of course, delay in the times that these different smartphones are receiving the signal, although the signal was sent at the same time, right? Is this delay useful in your calculations?
Okay, this delay might not be that useful. I'm not saying it's only useful, but it might happen that the weather condition in NTU and NUS is different. So the delay will be different. So so that's one problem in differential positioning, because in differential positioning the two receivers should not be very far away from each other, because the weather condition will be different. If there is it's raining at NTU and there is no rain in NUS, then there is no point of doing the differential positioning, because the weather condition is different. The water vapor will be more in NTU, less that will be less in anyways, or the other way around, because sometimes water vapor actually what we have seen that water vapor is more before rainfall. When the rain starts, it starts to decrease. So maybe if it's raining at NTU, maybe the water amount of water vapor is less, so that maybe the delay will be less. But there is another issue that there in case of rain, the delay also this rain water droplets will also introduce some delay. So the water as the weather condition is different, so the delay will be different. So it's better that both the users are quite close to each other. Yeah, but as we four people are sitting in this room right now, maybe we can use means uh, maybe the algorithm can use for these four smartphones to remove the delay or to calculate the delay. That is one quite possible thing maybe in future, but not right now
Yes.
because our smartphone receiver is not that powerful.
Okay. So like talking in general, right, about this whole research topic. Like, what's the ultimate goal? Like, what is the holy grail? What's it?
Holy Grail. Yeah.
Holy grail? Yeah. What are you trying to achieve?
So my main objective is to propose some algorithm which will using GPS signal which can accurately predict the weather. Right now, I am mostly focusing the tropical region. Maybe means in future I will extend my work for other climatic zone as well. So this is my main objective is to predict the weather for prediction algorithm. But okay, one thing I want to say that some people might ask one question that what's the necessity to propose a further model because already we can do that. So the first thing is that whatever we are using right now, it's not using GPS technology. It's some numerical weather models, which is a mathematical model, and it requires several inputs. So this mathematical models actually has been developed over several years, over plus 40, 50 years, and it uh, takes several inputs, and also it involves quite tedious computational processes. It requires very uh, fast, high powerful computers. So maybe I'm not claiming that my algorithm or weather prediction model using GPS right now directly can beat the numerical weather models that has been developed over the years. But maybe in future people will work more on this GPS technology. They will work with some different parameters and using several parameters together, several different models together. Maybe if we can assemble all the models together, then maybe that that final product will be quite useful or quite effective to predict the weather, or maybe it will be able to beat the numerical weather models. Then it means already we have deployed so many satellites all over the world, so many satellites in the orbit. So right now there are 32 GPS satellites. Apart from that, there are some other GNSS satellites like GLONASS, Beidou, Galileo. So as there are so many satellites, so all the time it revolves around the Earth, and the main advantage of GPS satellite is that at the very high spatial and temporal resolution. So wherever I will go, I will get the GPS signal. At each and every moment, I can receive the GPS signal. So this is one very big advantage. Another is that it can work in any weather condition. So even if there is cloud, I can receive the weather. I can receive the GPS signal. So these are the main advantages of GPS satellites. Why people are actually trying to switch from to some new technology or some new methodology. But because in numerical weather models, it's based on interpolation technique also, because an interpolation actually requires a very high and precise resolution. So if the horizontal or the vertical resolution that I am using for this interpolation technique, maybe it's not that accurate. So maybe it's not that useful. So maybe there will be some error. Though right now the numerical models that are being used, it's are quite effective, quite good, but still there are some problems in temporal resolution, because um, also numerical weather models is not a global model. There are different numerical weather models for different area and for different time. So that's why GPS signal GPS technology might overcome this issue, as because it means the same, at least the same algorithm we can use for different areas. Maybe we can we have to modify a bit, and also the spatial temporalization of the CPS satellite is quite high. It's quite important for a tropical station like Singapore, because in Singapore the numerical weather models it can't capture the very fast and rapid change in the weather dynamics, because as I've said that Singapore the weather dynamics is quite localized and it changes so fast. So, but due to this high spatial and temporal resolution, it will be means we will be able to capture those changes using GPS. So this is one of the biggest advantage of this technology. So, but right now I am not claiming that this GPS technology will completely beat the numerical weather models, but maybe we can at least we can introduce some of our algorithm into the numerical weather models to augment that thing, and we can expect that in near future or after some 10 or 20 years, maybe we will be able to use the GPS satellites to predict the weather, and maybe we can even use our smartphones to see the weather.
I see. And so the idea of using satellite signals for weather prediction, how old is it? Like, is it something new, or was it proposed from like a long time ago? Or
Not long time ago, that researchers have been working on this since 1995. So it's one or two means they have been working on this field for last 1 or 2 decades. So it's not a very old, but yes, it's not a very new topic either. But yes, still means the weather prediction has not been completely replaced by GPS technology. So a lot work has to be done in this field, but yeah, quite significant progress has been made on this field so far.
Okay, and so up to this point, the main technology that we have been using for weather prediction is numerical models mainly. And so for these models, what kind of input? Like, do you give them the historical data, or like how does it work?
Yeah, historical data is a very important thing in numerical data models. So they actually use those past data, which can show the trend, what going to happen during this time or for this particular region. At the same time, so using the past data, they actually train their models, and based on that, they actually give the new observations to the model. They feed that new observations to the model, and it this model give the based on that training, based on that past experience, it predicts the weather. So sometimes it might not work very well, but they actually they so in numerical weather models they don't just predict, they don't do one type of prediction, they do different predictions. So they just change the weather condition a bit, and then they do a second set of prediction, then change the weather the means the input means the input condition, initial condition they change a slightly, they change the initial condition, and then they create or they create a third set of predictions. So like that, they create several set of predictions, and based on that, they take an average or
Estimation.
of that, an estimation. So like that, they do this prediction. So
Right.
yeah, and this numerical weather model is not like that. You are using giving only the weather data, where they use some other models as well, like some ocean models, maybe the changes in the ocean, the sea surface temperature change. Maybe they also use the land surface model, like the amount of water has been absorbed by the land. They also use the radiation, the how much radiation has been emitted from the surface, how much radiation has been emitted from the ground. So they use all these inputs to the model. So they not only they use the atmospheric parameters, they also use those other parameters as well.
Mm. What about machine learning and neural networks and these new like considered like black box solutions to statistical problems? Are they being used in your
Yeah,
work?
they are right now. They are means extensively used in weather models. So I have also planned to use this machine learning in future. So right now, what I am doing, I am just trying to establish a statistical analysis and a threshold value for that. And based on that, I will maybe I will set several threshold value for different parameters, and based on that, I will train my model. And after that, when I will give the observation to my model, it will give me the prediction. So that is my aim right now. So as long so far I have actually set some threshold, or I have mostly I have done that statistical analysis to propose an algorithm. But maybe uh, in future I will train my model using that algorithm that I have proposed. And when I will give some new, I will feed some new observations to that model, machine learning model, it will predict the weather. So maybe in future I will actually, I want to implement that machine learning, because it's right now it's the most demanding technology.
Yeah.
Mm.
Yeah. All right. So as we approach the end of this episode, I would like to move on and talk about you, the person. So tell us a little bit about yourself and like what kind of things you enjoy doing or learning about outside your research area when you are not studying the weather or focused on doing your research. So what kind of things you like to do in your free time?
So yeah, research is something like it will. So as a person, I personally feel that some PhD is sometimes becomes very frustrating or
Sure.
depressing.
Yeah.
So I also means went through that phase, and for that you need recreation,
Sure.
some recreational activities. So I like to travel a lot. Though
Mhm.
due to COVID, I couldn't go outside Singapore,
Yeah.
but still I want to hang out with my friends. I want to explore some new restaurants,
Mhm.
and as I'm quite foodie, so I like to go to new restaurants, try to explore some new cuisines.
Mhm.
So yeah, I like to do that. Apart from that, I when I am alone in my room, so I watch movies.
Yeah.
I have Netflix Prime account, so I watch movies there. Sometimes I go to my friend's room and just chat like that. I do some adult chat with them.
Yeah.
So yeah, these are the entertainment in my life.
Mm.
I also like to listen to music.
Yeah.
What about student activities?
Okay, I am already in Triple GSC club. So last year I was the director of research showcase event.
Uh-huh.
So I organized that event. It's the actually the biggest event in Triple E department. So I organized that event, and
Can you tell us a little more about that?
yeah. So research showcase is an event where mainly we invite some keynote speakers
Mhm.
to talk about the ongoing technology that the current technology that the industries are using right now. And
Mhm.
also we invite several companies so that they interact with the students can get a very better knowledge about the industries, and they can be prepared themselves abo- according to the requirements of the companies.
Mhm.
Also, there are two other activities, two other uh, competition. One is 3MT competition that we organize
Yeah.
in research showcase event, and one is poster presentation competition. So we encourage the students to come and to submit posters or 3MT presentation slides. So where they means though means already 3MT is a requirement for the PhD students from
Yeah.
2019. So
Yeah.
yeah, so students they come up and they share their ideas, their research work, and also in the form of posters. Also, we invite the students to
Yeah.
present their
Present their
work.
work.
So that's actually it's a platform to share ideas to with one another, to make a connection with some other. people, to the industries. So yeah, we try to provide that platform to the students, the triple E students, so that they can get benefited from them.
Okay. All right.
All right. Thank you very much. I think
Thank you so
yeah,
much.
you gave us a lot of information about your research. But if there's anything else you would like to mention, if there's a question that we did not ask, please feel free to tell us whatever we missed with relation to your work, if you can think of anything.
I think I have means covered most of the points regarding my research. So right now I'm not able to think anything like that. But yeah,
All right, all right. It was
All
a
right.
pleasure. Thank you very
yeah,
much.
Thank you
yeah.
very much
Thank
for
you so
coming
much.
and
It was a really nice
sharing with
conversation
us.
with you. I also enjoyed this conversation a lot.
All right. Thank
All
you.
right.
Thank you.
Thank
Thank you
you.
so much.